Good, then let's continue. I should finish eating. Could you please close the door, and maybe you guys at the door also do something with this if you like, because now it's closed, which is fine. I don't care, but maybe it's nicer if it's not closed. Okay, so neurocognitive methods. And we are in the process of talking about the biological basis. I just realized that now with Arthur Jacobs' thing coming up, of course you also see kind of applications of the whole thing now, and you might have realized that a lot of things is in the methods, and the methods are often not fully described, but that's just how the things are, and the only thing that you can do against it is first of all study and learn methods, and then if you are writing papers, write them clearly and make sure that the literature gets better, and if you're reviewing papers, maybe ask them to state more clearly what they are actually doing. Good, so we are now talking about the biological part, and we went through functional hyperemia to the bold signal last week, and then ended up on the basic phenomenon that is the basis of all of these fMRI studies that you will see, namely the hemodynamic response. Is there something to clarify from last session that you would like to talk about? So we're picking up essentially at this hemodynamic response bit. No, okay. So there is a little bit of repetition, of course, also in the beginning. So the most important thing in terms of understanding what people are actually reporting when they are doing fMRI research, in terms of the biological mechanism, is the basic idea about the hemodynamic response, namely that in the resting state there is essentially equal levels of oxygenated and deoxygenated hemoglobin in the capillary compartment, and because there is strong level of deoxygenated hemoglobin, which you can see here with these little blue erythrocytes, there is considerable MR signal loss, which you might remember was detected by Ogawa in these rats that inhaled normal air as compared to rats that inhaled oxygenated air. Now, if there's activity, so there's neural activity, which is shown here as this brighter neural thing, what happens is that, of course, there are some energy demands, and the blood flow is essentially upregulated, yielding a higher degree of oxygenated than deoxygenated hemoglobin, which, because it basically washes out the deoxygenated hemoglobin, leads to less MR signal loss, hence a higher MR signal, hence neural activation. So neural activity up means MR signal up. Which is good because it's easy to remember. Neural activity up, MR signal up, but is a little bit surprising from the perspective of energy consumption, because now there's neural activity. One would think the neural activity eats up the oxygen and then rather lead to an increase in deoxygenated hemoglobin. This is not the case, which is a biological fact. But there are facts and then there's the truth, but I guess nobody watches Line of Duty. I'm currently watching Line of Duty. Anyway, it's a very good series. Or show. And then we discussed already last time that this is surprising. So blood flow increases, glucose metabolism also increases, but the metabolic rate of oxygen does not increase. So that's this uncoupling of cerebral blood flow and these metabolic rates. We talked about it, and we talked about that there are multiple theories. One of them is that it's specifically the astrocytes that are involved in this anaerobic glycolysis, as the astrocytes don't have mitochondria, but that there are a number of alternative explanations that one can, of course, build a research program on and investigate in further depth why there is actually an increase in oxygenated hemoglobin in the vicinity of activated neural tissue. And that's not quite clear, and is, at least in biology, some people might actually be doing research on that. It's not a typical cognitive neuroscience question. Yeah? So here in the cognitive neuroscience lab, you will not find people that look into that, because it requires different methods. In cognitive neuroscience, it's essentially taken as a given that increase in neural activity leads to increase in the MR signal, which you can also in your first fMRI experiment reproduce, at least for visual areas, because that really always happens. So this is also what we've seen last time, but I think we didn't see this last time. So this is where we start off again. So this shows the bold signal time course or the hemodynamic response, and it shows the hemodynamic response for two scenarios, one being a brief stimulation, which could be just a brief visual stimulus, like a picture of a face showing up and then going away again, or a quick cue to press a button or something like that. In general, when you see these both signal time courses, they usually refer actually to visual cortex. Then this immediately raises the question of if you model these time courses, whether your model should not be adapted for different areas and so on. And yes. But then it's also relatively similar over different cortical areas. We might see actually examples from frontal areas later on today, and you might see that this is roughly the case. So if there's brief stimulation, what one observes typically is a peak. So there's a rise and there's a fall. So the signal goes up and then it goes down again. That happens. And that happens in the order, and this is for some reason not shown here, in the order of seconds. So the peak is typically 4 to 6 seconds after the stimulus event. Yeah? So if you at time 0 have like a face showing up or a checkerboard, some bright visual stimulus, and you look at the visual cortex, then if this is brief, so let's say 500 milliseconds, then you observe in visual cortex, you observe this rise to peak after 4 to 6 seconds, and then falling down again. Additionally, fMRI and bold scientists model definitely the undershoot, so that after the rise to peak, the signal goes a little bit below baseline, and people debate whether there's an initial dip. So some people say there is an initial dip, some people say there is not an initial dip. In the end, it depends, I guess, on the precise stimulation scenario and the area and so on, whether you see this initial dip. Where these coming from, initial dip and undershoot, we will talk about later on, so keep that question in the back of your head for the moment. So this happens here around 4 to 6 seconds, and then we're going back to baseline, and then we are usually back to normal baseline after like 16 seconds or so. The whole kernel of the impulse response function when you model the thing with SPM is actually 32 seconds. So it's quite a long thing. The other thing that is a little bit more of historic relevance, unless you are using block designs for some reasons these days, is if you do persistence simulation. So you're showing one picture after the other or so, then what happens instead of having a fall after a peak is that you stay at a plateau for some time while there's still stimulation. So here we are more in the, let's say, this area here is more like something like 30 seconds or so, where you, after 4 to 6 seconds, come to a peak, and then because the stimulation is continuing, you go to a plateau. Although there might also be some adaptation, but once the stimulation is off, then it falls again, and there might be an initial dip or undershoot. Yeah, but the bottom line of all of this is, in terms of the bold signal time course, stimulus, signal goes up, signal goes down. Signal reaches its peak for a short stimulus, roughly 4 to 6 seconds after the stimulus. Yeah, that's the basic signal time course. You might come across in your papers that people talk about hemodynamic response functions. These also exist. These are modeling assumptions, so these are actually functions that are used to model hemodynamic responses. So it makes sense to clarify that what is shown here is supposed to be an idealistic version of data. The hemodynamic response functions, which are used to convolve your onset regressors in fMRI data analysis, they are mathematical models. We will come to that in January when we talk about GLM fMRI data analysis. And also in this part, some early on stuff. But that's usually reason for confusion in the beginning. Hemodynamic response with hemodynamic response function. The question of the initial dip, it's a debate. You can, if you look into, there's this neuroimage issue, 20 years of neuroimaging from 2012. It's a nice thing. So there are short articles in there on some historic issues. There's also some historical review of the initial dip. It's one of these things where people, some people say there is an initial dip, other people say there's no initial dip, and then they have their findings. This is data in favor of an initial dip. The question is, what is this initial dip? Where does it come from? The idea that is put forward is that this initial dip might actually relate to early and spatially specific increase of oxygenated deoxygenated. That's what I mean, right? So oxygenated means going up, and so I think here I confused myself. And this is the point that that in some voxel it might be the case that actually the energy response lowers the oxygen level. So that's essentially happening before the oxygenated blood rushes in and leads to a decrease in the signal. The thing is, I did fMRI of visual cortex, and using a certain stimulation and measurement protocol, we didn't see an initial dip, so I don't know whether there's an initial dip.
Is it oxygenated decrease or deoxygenated increase?
So this is one. Yeah, you're right, sorry. Yeah, so it's oxygenated decrease, meaning deoxygenated increase. You're right, yeah. So I just confused myself twice. Very good. Yeah, but the idea is that it's that there actually it's happening what one would expect, that if there's neural activity, metabolism goes up and oxygen is removed from the blood. It's an open story. The standard model of the hemodynamic response, this 2 gamma function, does not model initial dip, and I think nobody nobody makes a fuss these days if somebody does not model the initial dip. So initial dip is kind of a 90s thing in a way. The post-stimulus undershoot. So this is going to baseline, below baseline after stimulation, and this is actually modeled in the standard models in GLM analysis in this 2 gamma function, no, not gamma function, but gamma probability density function models. And there the idea is that this can be explained by what is called the balloon model. The balloon model itself is actually formulated as differential, as a set of differential equations. We will see the balloon model in all its glory when we talk about DCM, because dynamic causal modeling. Has anyone prepared DCM paper in any of your courses? You don't know. So, no, I don't ask now what kind of things you're discussing with Arthur. Or still, I'm interested. Is there anyone for this weekend? Does anyone prepare something that has GLM FMI? Yeah. Yes. Does anyone has something that has MVPA FMI? Pattern classification yes, also. Anyone has something, but the others not. Does anyone has something with DCM or computational FMI? What are you doing in this class? Not FMI at all? Which class? Good morning. Arthur Jacobs class this weekend. Yeah, but you have your papers that you're presenting. And have you looked at them? Yes. Okay, good. Okay, so but you don't know whether it's FMI. Is it all EEG or what is going on? EEG. Ah, it's all EEG. Ah. We have FMI. We have 2 EEG papers. Oh, okay. That makes sense. Do you have oscillations in these EEG papers? Yeah. Classify. So you have MVPA classifier on EEG. Good. Yeah, very good. Okay, I don't want to talk about that because it's on tape. So we talk about the balloon model, and we will talk about the balloon model, like I said, in its mathematical form and the real meat of the balloon model when we talk about DCM in FMI in the summer, because DCM is essentially an extension of the balloon model. We give some intuition right now. So the balloon model tries to explain why the bold signal goes below baseline after the end of signal stimulation. And the idea is as follows. First, neural activity starts. This then leads to an increase of blood inflow, leads to a surplus of blood inflow to outflow. So there is an increase in the blood volume, yeah, in this venal compartment, but with more oxygenated hemoglobin. But it's there's a little bit of yeah, it's like a balloon filling. So then the neural activity stops, and the blood flow decrease is larger than the blood volume decrease, meaning there is now an increase in the volume of venous blood, which in the meantime is replaced by a deoxygenated hemoglobin and hence negative vol. So it's a dynamic model. It's really not that meaningful actually from this slide, because to really appreciate it, one needs to go over the differential equations. The idea is that there's kind of, it's like a it's stored, so the stuff comes in, and then at one point the oxygenated, so the deoxygenated hemoglobin is there's even more deoxygenated hemoglobin as in the beginning. I mean, this is the only reason, of course, why you would have a negative thing. So here, this is at baseline. There you have a certain ratio of oxygenated and deoxygenated hemoglobin. If you have something negative, of course, you must have a surplus of deoxygenated hemoglobin, so if more signal dropout. And of course, yes, this must be because for some time there's an increase in the volume of deoxygenated hemoglobin. And this is what this balloon model tries to explain with a dynamic system, which is formulated in terms of differential equations, which we will see in its real form once we talked about differential equations. The thing is also the post-stimulus undershoot is not really undebated. There, of course, this depends on measuring cerebral blood flow and cerebral blood volume. So you must have the means to measure that, for example, using neuroimaging. And some studies find actually that there is this mismatch in terms of the cerebral blood volume, so that the cerebral blood volume stays up after the end of stimulus presentations, but other studies actually find that this is not the case. So again, like with the initial dip, it's something that people debate. It's not that something that you will find studies that are in favor of the initial dip and some that are not in favor of the initial dip. With the balloon model, because it's actually it goes into the modeling assumption, it's a little bit less contested. But then you also find camps that say post-stimulus undershoot exists, and others say it doesn't exist, and then they have the theories why that is. Yeah? The bottom line is, and this is why I said in the beginning, stimulus or task or whatever comes on, signal goes up. This initial dip, post-stimulus undershoot. Yes, maybe not. Yes, maybe under certain conditions. More important actually than this post-stimulus and initial dip business is the fact that you appreciate that the bolt response does not always look completely the same given the same event. And this is actually much more important to actually get a feeling for the system, for the signal. So this shows motor cortex, a single voxel, 2 seconds of hand squeeze every 16 to 18 seconds. So there's actually quite a long break between the squeezes. So what you can see here is now there's the signal going around a little bit. Of course, this has an initial dip as if you look at it. So here there would be some squeezing. Squeezing happens. Sometime later, the signal goes up. Signal peaks around 4 to 6 seconds after the squeezing, and then goes back. And here you also have a bit of a undershoot if you want, if you look at this. But of course, one would need to average and see whether this actually holds. Then you're back essentially to baseline or a little bit below. Next squeezing, signal goes up again. Signal goes down again. And then next squeezing, signal goes up, and then here it goes quite a lot down. And then next squeezing, signal goes up again, but somehow it stays up here a little bit, and then so. And you see, and this is the important thing, if one cuts this out, so if one now isolates these squeezes, so here's the hand squeezing, and looks at the single trials, you see that there is considerable variability in the single event measures. Yeah? So this is a typical EEG, ERP analysis, if you want, where you just cut out the signal around the event, and you see these different events here and all these different traces, and you see that roughly the signal is going up, and then it goes down. Sometimes it goes below baseline. It looks a little bit, there's a majority of trials that actually go below baseline, but also on a number of trials it doesn't go below baseline. And well, initial dip, I mean, if the squeezing is happening here, I'm not sure that I see an initial dip of the signal. What I see is more a trend to go up all the time. The important thing is it's variable. Yeah, it's not that, because if one looks at the textbook example of this is not how the signal looks on a given event. Yeah? So this is how signals look, at least in terms of this sampling rate, which is here TR of, oh, that's actually quite fast. It's 5 seconds, so 6 seconds, here's the peak. So here we have measurements, I think every second. So it's a TR of 1 second, I would think. Yeah, but the important thing is signal variability. It's also a very good, if you do GLM analysis, or even if you do classifier analysis of this, to look at individual voxel time courses, to appreciate that this is really variable. Good. Yeah.
When the signal is below baseline, what does it mean?
It doesn't mean anything. So the whole thing with the MR signal is that it's not a quantitative thing. Yeah. So when we talk about the imaging process a little bit more in January, this is all normalized to some. So the typical the raw. So remember again that the signal derives from these images that you take, yeah, and you have these gray level images that are taken over time, and these gray values of these images, they are do not relate in any meaningful way to some physical unit. So they are not that, for example, if you kind of, one could imagine that there is kind of a water content in the brain, which there is, of course, and if you would measure that using chemical means, but somehow in an animal, let's say, you cut out the brain and measure how much water you have in that by dissecting it and somehow getting the water content out, you would have a very hard time to relate this water content to an MR signal, because it goes to the process of Fourier transform. It's all related based on this original net magnetization, and the units that translate this into the final image, they get lost. And this is, I think, what most people, I mean, people try to get this into a quantitative framework that actually relates to physical quantities, but that's not how it is right now. This also means that the MR signal that one looks here at is in arbitrary units, and that it's below 0 means just that it's below the average, however the average, in whichever way the average was computed here. Maybe there was a little bit of baseline in the beginning and the end, and this goes into the average and so on, and this is then percent signal change with respect to this average. So this is again in the same way in terms of signal goes up and signal goes down. In general, these signals changes, and we'll come later to that, they are, in terms of percentages, they are quite low. So it's like a 4%, 6% signal change, but it doesn't relate to anything quantitative. And it definitely, one should not try to explain this in terms of neural activity that is lower or higher or something. That's there. Although actually I think I'm actually on a paper that argues for this negative bold and positive bold related to more or less neural activity from our old Birmingham EEG fMRI studies. But that's really, there are also studies that go in this direction, but I would always be very careful, because there's so many steps in terms of the signal processing between data acquisition and these kind of plots that it's not a reliable physical unit. Okay, nevertheless, there are neural correlates of the bold signal, and this is of course of interest in terms of interpreting these changes. So think again that how this all came about is that early on there was this Ogawa finding, and then people put so Kwong, Badettina, and Ogawa put humans in the scanner, showed them visual stimuli, so vortex stimulation, and observed that the MR signal goes up. Yeah, so it was not, the way this was not done was that they had somehow some kind of phantom or maybe an animal experiment where the neural activity was measured and for a long time, and everybody knew what the neural activity means and so on, and that was really completely explained, like human visual cortex. And then neural activity had been fully characterized, and then MR came along. This is now not how this works. How this works is you put a person in the scanner, you show them visual stimuli, MR signal goes up, which of course leaves the question open what on a neural level the MR signal actually relates to. Yeah? This might be surprising that this is not completely clear, but this is just how science progressed in this way. Because that's a latent state, if you want, in these experiments. Yeah, so you assume that with the visual stimulus you induce neural activity, which then induces changes in metabolism, which then induces changes in the MR signal. But what exactly that is unclear, and it's still unclear. And the reason why it's still unclear, and also will be unclear for a long time, is that it's not really clear what neural activity actually is. But that's a different issue. So. There has been, however, a very famous study in the early 2000s by Nikos Logothetis. Have you heard the name? In which context?
Both the study and the monkey
business. The monkey business. Yes. Yeah, so when I entered the field, there was just it was very uncontroversial, so the whole department, so it was just an awesome department. And recently there has been some uproar also with regards to this department, and there are many views on this in terms of animal welfare. But the good thing is the circus gorilla, monkey, orangutan can stay with his circus. That's the good news in terms of animal welfare. You don't know about this. Some people know. You don't know? No. There's Ronnie, the oldest chimpanzee in a circus in Germany, who was 47, who grew up with the director or the head of the circus. And then there was this animal welfare people, and they said he should now be moved to Holland or to the Netherlands and be re-socialized with other monkeys. And then the circus said, no, he has been, this is horrible, the poor monkey has been with humans all his life, and now it needs to be with other monkeys, and this might be bad for the old monkey. And then judge has ruled the old monkey can stay with the humans. Why don't you know these things? Anyway, this was just recently. Okay, but then going back to the science that was done here, early 2000s. So the question is, if we would have the possibility to measure at the same time neural activity and bold activity, what would bold activity be most related to? And this is also one of the reasons why I did, no, not really, but I did EEG fMRI, so where you also have these two things, and people are always interested in how these things are related. Here it was done simultaneously, so what you see here is the visual cortex of a macaque monkey in a scanner. Here you see an electrode that is essentially poked into visual cortex. This monkey was at the same time in an MR scanner, so that's a monkey MR setup that they built for this purpose in Tübingen, and they also measured T2 star values, so bold contrast, and tried to figure out what the relationship is between the bold response and neural activity. And then the question is, of course, what is neural activity? So here you put an electrode in, so you essentially record broadband signals of all sorts of frequencies, and you can filter them differently. And what is shown here is actually the raw signal from the electrode. What happens here is that there's a visual stimulus. Here you see the stimulation, and then you see the activity in terms of electrical activity at the electrode, and you see the bold response in this greenish area here, which this is quite a long stimulation, so you see it's 10 to 20 it's almost 10-second stimulation, which looks a little bit different definitely from what we've seen previously, but it shows that it goes up, stays up for some time, and then goes down again. And that's the percent modulation in bold, which is actually quite low. Now, yeah, so it's a simultaneous invasive electrophysiological and EPI recordings in monkeys. The stimulus was a checkerboard, so black and white stimulus recordings from V1. Now the question is, what is done with this data from this electrode? And there, neurophysiologists try to make everyone believe that they exactly know what they're actually recording there. So essentially they record the same thing as if you put an electrode on the scalp, but they record it a little bit less filtered by the scalp. And then they add additional filters, for example, by looking for spikes, or what in this case is called multiple unit activity, which they think, and this is the theory, like you can have a theory about what the EEG signal means, they have a theory about what the electrical signal means if you have an if you have an electrode here. If you filter them in one way, you have multiple unit activity, which is understood as the output of a neural population within a couple of 100 microns of the electrode tip. So important thing is here output, if you want action potentials. On the other hand, they measure local field potentials, which is just in a different frequency band of the signal, the broadband signal that they record here, which they believe, like people that put the EEG electrodes on the scalp, that this is the synchronized dendrosomatic neural input to an area. So the important thing in terms of the story is you put the electrode there, you look at the signal from the electrode in different frequency bands. One you call multiple unit activity, the other one you call local field potential, and associate one of them with the output of the area, the other one with the input of the area. And then the question is, what happens now with regards to input and output and the bold signal? And this is shown here. So if you present a stimulus for 24 seconds, what happens is that the multiple unit activity and also what is called the spike density function, which is spikes over time, they adapt quite quickly. The local field potentials, they stay up. Yeah. So somehow the spiking output of the visual cortex is done after quite some time, because, and this is a general finding, because most of neural activity is actually signaling changes, and the changes here, a stimulus comes on, and then if stimulus stays on, there's not that much new stuff, so no surprise, no change in the external stimulus, so neural activity goes essentially back to baseline, but the LFPs still stay up. So the input to the area is still stay up, but it's not, if you want, a full story behind this, if you want, is that V1 is sent out that the checkerboard stimulus came up, and then this checkerboard is still on, but V1 has already told the rest of the brain, checkerboard stimulus is on, have fun. I tell you when checkerboard stimulus is going off, but still registered the local field potential. Bold signal stays up at the same time as the local field potential stay up. And this is similar here for shorter stimulation. And then, of course, if you're going into even shorter stimulation, then also the local field potential is not anymore. The thing is, the main finding from these studies is that there's a fast adaptation of the multiple unit activity and spike density function, so the spiking output, but prolonged presence of local field potentials in bold. And this is the main finding of this. So it's not in terms of a correlation between local field potentials and bold or something, but it's this, that the spikes adapt quickly and local field potentials don't adapt quickly, like the bold signal, that then yields this basic idea that the bold signal correlates, or not correlates, but reflects the input to an area in terms of local field potentials, whereas whereas it doesn't reflect the input. The problem is, of course, in these studies you also have quite a covariation between input and output, so it's not that clear, but still it's the basic story. Yeah? So the basic story is that you have that in terms of neural activity, if you believe that local field potentials are the input to an area, then bold signal is more associated time-wise with local field potentials. What they actually did later on with the same data, yeah?
Isn't the multiple unit activity the input? Because it doesn't prolong over time, and the local field potential is output. No, the input, so spiking is always output of an area. Yeah. So if you detect spikes, that's the output of an area. The local field potentials, so these are the dendritic activities that are the input to an area. So the thing is here, stimulus goes on. The input in terms of local field potentials at the dendrites from incoming axons at the dendrites is still happening, but the output ceases. So the bold activity and the input, they are on simultaneously. The output is done quite quickly. So it correlates with the 24 seconds in IR.
Yeah, this is what this is supposed to show. So the thing, I wouldn't call this correlation, because in correlation one always would think that one actually computes a correlation coefficient and so on. So it's just that they, and this is really, if you read these papers carefully, and also Nikos Logotheus' interpretations of them, this is exactly what he says, that it's just that they are on over the same time. Local field potentials and bold are more, if you want, correlated in time than bold and multiple unit activity or spiking activity. Yeah, because one can compute many correlations between many features, and the main interpretation of these studies relies on the fact that they are on at the same time. What they did later on with these data is also, I think they actually did that after we did the same thing with, or around the same time maybe, we did the same thing with EEG and fMRI in terms of looking at correlations using mutual information. That has to do a little bit with the fact that electrophysiologists liked mutual information, and then Stefano Panzeri, who did kind of this mutual information, he was in Tübingen at one point. So they, of course, with this electrode that was in this V1 region of interest, you had not only multiple unit activities and local field potentials, but you could, of course, do a full spectrogram of this signal. So you could do a Fourier transform of the whole thing. What is done here in addition is that you do the Fourier transform not only at a single time points, but over multiple time points. And then you get what is called the spectrogram, which you get out of the Fourier transform. So you get the power at different frequencies. And then you can look at the gamma, beta, and alpha frequencies and local field potentials, which are a mixture of these, and look what is correlating with the bold signal more or less. And this is shown here, and here it's specifically the gamma frequency that shows strong correlation with or strong mutual information with the bold signal. And there I always have to get it right, and at one point also put it into the slides. This is from EEG fMRI studies. If I'm not mistaken, this is also the current idea that I hope I'm not mistaken. There's definitely a covariation in terms of gamma and alpha power and the bold signal. Gamma, I think,
is associated with an increase of bold signal. Alpha is associated with a decrease of bold signal. Here what is shown is mutual information, which doesn't have this sign. So here they are both associated, and it just shows that gamma is more associated with the bold signal. In terms of alpha and bold signal decreases, that also makes sense if you know a little bit about EEG, and that alpha is associated with this dosing or closing your eyes and so on. So that makes sense in terms of alpha signals, that the whole system is not in power mode. So it makes sense to have this associated with less bold signal. But these are the results from EEG fMRI studies that look into the neural correlates, and they are of course not as immediate to neural activity as is an electrode that is in. But essentially, this is the current state of affairs. So the old stuff, more talking about local field potentials, input, multiple unit activity, spiking output, and the association with bold. The newer stuff more talking about the association between certain frequency bands, so certain oscillations, certain frequencies, hence Fourier analysis and all the stuff we did this morning, with the bold signal. Yeah? And in the end, and this is also of course what exists, but it's not that used much. The only thing that you really can make a sense of these measurements is if you do a model. Yeah? And of course there are models around, so you can of course have a neural model and then also do a neurovascular coupling model, for example using the balloon model, and we will see some of this in the summer term when we model things, although their neural activity is really quite simple. And then based on this model, testing this model on this kind of data. From just doing correlations all the time, of course, you don't get into mechanisms. However, you need these correlations also to know something that makes sense to start modeling and have these results. So I think in terms of gamma, alpha variations with bold signal, that is fairly established by now. Was there a question? No. Good. Other questions? No. Good. This is also, I always think about the exam, which is maybe not good, but these neural correlates of bold signal, they are also often forgotten when I ask about them. Yeah, but I think they are important. So please also, when you prepare for the exam, also study those, because you will also have, what you will find is that if you ever go to interdisciplinary conferences where there are also neurophysiologists, they really think so it's kind of from the 90s and so on. So when imaging first started, neurophysiologists were a little bit annoyed because good people would do neural imaging rather than doing neurophysiology, and of course also funds went into neuroimaging and neurophysiology, and they still, and some of them still, not Nikos Logotidis, he has quite a reasonable view on this whole thing, but there are neurophysiologists who think what I measure with my electrode, that's the truth about neural activity, although they also don't really know what they measure there. And what they do in imaging, that's nobody knows what they do in imaging, what this kind of signal means. And this is just not true. So neither they, nor EEG people, nor fMRI people really know what they are measuring. Nobody knows what they are measuring because it's just a signal, right? So this is this thing that the signal and the data, they are part of the scientific realm. If you watch my first GLM lecture, hopefully by now, where I talk about this whole modeling business, signals are always part of the science bit of things, and what is really out there you will never know, and also neurophysiologists don't know that. But yeah, but you will sometimes need to stand up to neurophysiologists and tell them that they also don't know what they're measuring or something. Maybe don't be so confrontational. But the good neurophysiologists, actually, they realize that. Okay, then let's have another break and then start with the spatial temporal details. So,